So today my lecture will be devoted to the proof of Van Danzig's theorem, which is one of the most important theorem in the theory of totally disconnected locally compact groups. And then we are going to use this theorem in order to produce examples of TDLC groups. So this is the goal for today. Okay, let's start. So let's see the statements of this theorem. Van Danzig proved in 1936 that if G is a totally disconnected locally compact group, then every neighborhood of the identity contains a compact open subgroup. This means that actually TDLC groups are full of compact open subgroups. This is not a trivial property, and it will turn to be the property on which many techniques that we now use to investigate this group are based. So, okay, let's go with a proof, because I think that it's important to see at least once in the life the proof of this theorem. So, proof. I need to start by using a theorem which is from, let me see the name, Edinburgh. Hopefully I'm pronouncing correctly. Theorem. This theorem is about totally disconnected locally compact group being zero dimension. So I don't want to talk about this property now, but I'm just going to use this property in order to claim that I can always find, so there exists compact open neighborhood K of the identity in G. So we know that the group is locally compact, so we know that there exists a neighborhood which is compact, but by using this theorem, we now can choose a neighborhood K which is also open. But we want to prove that actually there is something compact open inside, but it has to be a subgroup. So I'm going to construct a subgroup containing K. Let's see. Okay. Let's use all the properties coming from G being a topological group. So we have that left translations. No, this is not translations are continuous. So this implies that whenever I choose an X in K, I can always find an open neighborhood of the identity. So this one is open, such that X UX is contained in K. Now I want to make this set even smaller. So I use the fact that multiplication is continuous. And then for any X in K, there exists a Vx which contains G open, such that the product Vx Vx as a set is contained in Ux. And now I use the fact that inversion is continuous to claim that for each x in K, the x can be chosen to be symmetric, which means that the x is equal to the x minus 1. Okay? Okay, now let's have a look at K. K can be written, I cannot write, but K can be written as a union of elements, as a union running over all possible elements in K of the sets XVX. But K is compact, so we obtain that there exist finitely many x1, xn in K, such that K is covered by x1 vx1, you know, actually is equal, but okay, beyond xn vxn. And now that we have finitely many of those, we can set V to be the intersection of this finite number of open sets. So in particular, V is open and symmetric, because each one of those were open and symmetric. Okay, now let's see the subgroup that I want to build. So how this V is going to play a role. We define H to be the union over all possible natural numbers of products of V. Of course, we do this m times. And then we note that H is a subgroup because V is symmetric, and H is open because V was open. So we need to prove that is H compact. In order to prove that H is compact, okay, the answer will be yes. But to prove it, we prove that H is contained in K. Why is this enough? The fact is that K is compact and H is closed, because H is an open subgroup, and then we saw yesterday that open subgroups are always closed. So if we succeed in proving that H is contained in K, H is going to be a closed subset of a compact set, so it's going to be compact, and this will finish the proof. Okay, so let's do that. I want to prove that H is in K. So since H is union of products of V, I want to prove that each one of these products is contained in K. To do that, I need to have a look at what is happening to K times V. K times V is nothing but the union over, so I is running from 1 to n of xi vxi times v, but this is contained in the union of xi vxi v, which is contained in the union again. Now v, so this guy here, this v is contained in vxi for each I, so I can just write here again vxi, but now we choose vx in such a way the product is contained in ux. So actually this one is contained in uxi. So this is contained in the union of xi xi. And then I go back again and I check how did I choose ux, and this is the translation, so this is contained in k because each one of these is contained in k. So I obtained that k times v is contained in k, and now I can use it because v is nothing but 1g times v, which is contained in k times v, because k was a neighborhood of the identity. So the identity is inside k. So we have this one. Now we go, let's say, by induction. So let's see how do we do this? So v times v. V times v now is contained in what? So this is contained in k times v times v, because v, so this is contained in k, sorry. I missed the last part. So v is contained in k times v, which is contained in k, which is what I just proved. So I should correct this. Okay. So I can just substitute v with k, and this is time v. But now again, k times v, by using this formula, is contained in k. And then I keep on going, and in the end, I have that v times v n times is contained in k. And this concludes the proof. And okay, so this is the end of the proof of Van Dansing theorem. Okay, so let's have a look at all possible consequences that we can have now that the theorem is available. So the first consequence is the following. G is a locally compact group. Then we look at the identity component, so the largest connected subset containing the identity in G. And Van Dansing theorem implies that the identity component is now the intersection of all open subgroups of G. I'm not going to prove this proposition, but I want to have a look at a corollary of this proposition, which is can be seen, regarded as a characterization of totally disconnected locally compact groups. So a topological group is CDLC if and only if it has a neighborhood basis at identity consisting of compact open subgroup. So we already know that this implication is nothing but Van Dansing theorem, because we have just proved that every neighborhood of the identity contains a compact open subgroup. And this means that the group has a neighborhood basis at identity consisting of compact open subgroups. So actually what we want to prove is the other implication. The other implication, so suppose there is B. Okay, let's see, coincide. Okay, there is B made of there is B, which is a neighborhood basis X1 of G, such that all elements of B are compact open subgroups. Okay, since we have compact neighborhoods of the identity, the group is locally compact. So this is clear. We need to prove that the group is totally disconnected. So in order to prove that G is totally disconnected, we prove that the identity component is trivial. But how do we do that? So we just noticed that 1 over G, this is the intersection over all elements of B, because this is a neighborhood basis. So the intersection is going to give you the point they are neighboring. But in particular, each H is an open subgroup. So this contains the intersection over all possible H in G open. But by the proposition, this is exactly G naught. So G naught is contained in 1G, and this concludes the proof. Okay. So now we know that whenever we have a group with such a basis, then we can directly claim that this group is totally disconnected and locally compact. And this is what we are going to do in the second part of the lecture, when I will present some examples. Okay, let's see a second consequence, because I was talking about this yesterday. So yesterday, 2 days ago, last lecture, I concluded the lecture claiming that profinite groups are the compact case in the category of totally disconnected locally compact groups. One implication was clear, because every profinite group is both compact and totally disconnected, but we need the reverse implication. And this is what we are going to do now by using Van Dantzing theorem. So I want to prove that if I start from a group which is compact and totally disconnected, then I get something profinite. So proof, this is easy as well. Okay, we use again Van Dantzing, but they are all consequences of this theorem, so clearly we're going to use it. And then we consider B to be the set of all subgroups of G, such that H is compact and open. And we know that this is a basis at the identity. Now, I just pick one element and I look at what is happening at the core. This is the normal core of H in G. This is nothing but the intersection over all elements in G of G, H, G minus 1, which is a normal subgroup in G. Then what else can we say? HG is open. Is open in G because H was open and G compact. This means that H has finite index inside G. So there are only finitely many conjugates of H in G. So this is a finite intersection of open sets. These are open because conjugation was open. So this is a finite intersection of open sets. So this is again open. And in particular is open, and this means that HG is closed, and so compact. And I can do this for any H. So for an arbitrary H in B, I can always find HG, which is normally in G, is open and compact, and it is contained in H, because in particular, this one is contained in H, because H appears in this intersection. So this means that if I consider N, which is the set of all normal subgroup in G, such that H is compact and open, this is again a basis of neighborhoods at the identity. But now, if I consider the canonical continuous morphism from G to the inverse limit of G mod H, where H is in N, this is surjective, but these are all finite groups. So this group here is profinite, and then phi is injective because the intersection of all H in N is trivial because this is a basis at the identity. So actually G is a profinite group, can be written in this way. And any continuous map between compact things is open, so this is a topological isomorphism. Okay, so this is how we see that profinite groups are compact TDLC groups. Then Van Dancing can be used again to prove that if you quotient a totally disconnected locally compact group by something close, then you get again totally disconnected locally compact groups. This means that whenever you are using these groups, you are going to care about closed subgroups. So closed subgroups are the ones that are still in the category, in the right category, because they are still totally disconnected and locally compact. And also, if you quotient by these groups, you obtain again something in the category. Okay, so there are questions so far. Everything is clear, probably. Let's go to treat some examples. We have already seen that discrete groups are profinite, but I want to stress further this part. are profinite and are not profinite, are totally disconnected locally compact. And profinite groups are again totally disconnected locally compact groups. Then another example is given by the class of local fields. I mean non-discrete, non-Archimedean, locally compact fields. This should be a field here. An example of this kind of fields is this is the field of periodic numbers for a given prime P. And how do we see that this is totally disconnected and locally compact? Okay, there are various ways you can do that, but from the point of view of Van Dantzig theorem, we look at the basis at the identity, which is given by, so ZP is the unit ball in QP, so I can just go down, make it smaller and smaller, so N is in N, and this is a neighborhood basis at 1G, and then we just remember that the P, it is profinite because ZP can be viewed as an inverse limit. So this is an inverse limit of all P-quotients of Z. And the same is true for Pn times Zp. So these are all compact open subgroups in QP. And so QP by Van Dantzig theorem is totally disconnected and locally compact. But okay, this is roughly speaking because we have to prove that things work fine. But I just want to remark on the basis now. Okay, so let's see the example given by automorphism group of a connected locally finite graph, because this was the first example I gave about of a topological group. And now today I want to prove that, or I want to give you an idea of how it is possible to prove that this group is totally disconnected and locally compact. And we are going to use Van Dantzig theorem. So just recall that gamma is a locally finite graph which is connected. So locally finite means that each vertex has finitely many adjacent vertices. And connected means that whenever you pick two vertices in the graph, you can always find a path which is connecting the two vertices. The automorphism of gamma, an automorphism of gamma is a bijection on the set of vertices which is preserving the adjacency relation. And all automorphisms, of course, form a group under composition. This group is topological, and a basis for the topology, or I have to say a neighborhood basis at the identity of the topology is given by this one. So I have to choose V to be a finite subset of vertices, and then the set sigma V is nothing but the point-wise stabilizer of this set. So this means that in sigma V, you can find all automorphisms of gamma that fix point-wise the vertices of V. So they are point-wise stabilizers of finite subset of vertices. These are open, these are subgroups. So in order to apply, let's say Van Dantzig, I have to prove that these are compact. Once I have this property, I can conclude that the group is totally disconnected and locally compact. So let's start with the idea of how do I prove this. The first step is to reduce to stabilizer of single vertices. So the fact is that I want to prove that each element of this neighborhood basis is compact. But so let's suppose that V is equal to V1, V2, then sigma V is nothing but sigma of the set V1. So on constructing sigma of the set V2, where these two guys are the stabilizers of V1 and V2 respectively. Okay, so this means that the pointwise stabilizer of a finite set of vertices is the intersection of the stabilizers of the single vertices. But so if I'm able to prove that sigma V is compact, then sigma V will be, because it is an open subgroup of a compact one. Because sigma V is contained in the single vertex, the stabilizer of the single vertex. So if this one is compact, then this one is open inside the compact one, but open subgroups are closed. So again, this one is compact. So it's sufficient to prove the claim for a stabilizer of single vertices. Okay, this was, maybe it was much more intuitive, much more difficult to
sorry, what was this pi here?
What was the
pi?
Subgroup I?
Pi.
Pi.
This last sentence of this page. You talk about some pi.
It says it, not pi.
Huh?
It's it.
So so this is it. So this is it is not pi. Probably this.
Ah. Oh, okay. Sorry. Stupid question.
No. Sorry. Sometimes, so when it is not synchronizing very well, the
okay.
my writing becomes terrible.
Okay, well now I get it.
Okay. Thanks. Okay, so now we have just to worry about the stabilizer of a single vertex. So let's have a look at this guy. So now we are considering this group here, which is the stabilizer of the single vertex V. I draw here a very nice locally finite graph. This is very regular, but just because things works easily, if I have to draw spheres around V. So what do I mean by the term sphere? Okay, this should be quite intuitive as well. But if I fix a vertex V in a graph, I can always, in some sense, talk about a distance from another vertex X in the graph from V, because since the graph is connected, then there is always a path connecting the two vertices. In this case, I can count the number of edges that form the path, and then I can choose the shortest path, and I can define the length of the shortest path, the geodesic, as the distance between the two vertices. So actually, we can regard a connected graph as a metric space, a geodesic metric space. In particular, since I can do that, I can, as usual, define the sphere around a point as the set of all elements that have distance less or equal to some given number. This means that I'm just, if I'm good enough, let's see. This means that I can just consider these spheres around V and then I consider all the points that have distance at least, in this scenario, is at least 2. Okay? Now, why this is important? Because now the graph is locally finite. So whenever I zoom on a neighborhood, a sphere of V, this is a finite set. This is a finite set, and this is going to be helpful in the third step, where I want to create a group morphism from my G. Oh, this is not G. This is the stabilizer. So I want to form a group morphism from the stabilizer of V to a compact group, and so and then prove that this morphism is continuous, open, and injective, and then I will conclude that sigma V is compact. So this is the goal. How do we do that? So we notice that for each n in n, sigma V acts on the sphere, because we are keeping V fixed, and so all the stabilizer can do is just moving the elements in each sphere among them, because you cannot break the graph, so the distance cannot change. So actually sigma V is acting as a permutation on the sphere. Okay, let me keep some notation. So this means that I can define a map phi n from sigma V to the symmetric, the set of the permutation, the group of the permutation of the sphere. And please notice that this is a finite. This is a finite group because the sphere is finite. Now I want to do this for all n at the same time. So I build phi from sigma V to the product over all possible n of these permutation groups here. And this group now is compact by Tikhonov theorem. And the claim, I'm not going to prove it, but you can find it in the notes, that phi is injective, closed, and continuous. And this is going to be enough to prove that phi is a topological isomorphism of the stabilizers, of the stabilizer of one point onto a closed subgroup of this compact group. And this means that sigma V is going to be profinite. Just to be clear, here I'm sending each element G to this family, just to be very clear, but I think that was fine. Okay, so this is the idea of how you can prove that each stabilizer is compact. So in the end, we got that the automorphism group of a locally finite connected graph admit a neighborhood basis of identity formed by compact open subgroup. And so it is totally disconnected and locally compact. Now I want to just introduce another example, which is a famous example, because we, in order to prove that the group I'm going to introduce is totally disconnected and locally compact, actually we are going to use, or the important step is that this group here, the automorphism of a locally finite connected graph, is TDLC. So let's have a look. I will spend the last time on this example because even if I'm not going to be, no, I don't want to say precise, but I'm not going to give all the details. I want to present this group because it's quite important. Okay, the name of this, I should say, family of groups is narrating, the narratings group of spheromorphism of a deregular tree. Okay, these are complicated words, but nothing so awful. So let's start by introducing some terminology, or at least repeating a few things. What is a deregular tree? A deregular tree is a tree whose vertices have valency, there is missing valency, whose vertices have valency d+1. Here you can see a few examples. So d is equal to 3, so I want each vertex has to have 4 neighbors. I don't want to make them look like. So there are 4 neighbors for each vertex, and so on. And here these 2, so we have 3 neighbors for each vertex. What happens when the deregular tree is rooted? When the deregular tree is rooted, we want the root to have d children, and all other vertices they have to still have valency d+1. So what do I mean is the following: if d is equal to 3, then you can see that you can have a look at the tree from the top to the bottom. So the root has 3 children, and then any other vertex has the same number of children. So you have always 3 children. But then, of course, the valency for vertices that are not the root is 4, because you have the root or the previous vertex as the +1. So this is why you have this distinction between the root and all the other vertices. So in some sense, this convention, deregular, means the number of children. So if d is equal to 3, you have to draw the graph, the tree, in such a way the number of the children is equal to d. Okay. Now, what happens? So these are examples of infinite deregular trees. Let's see what I'm going to mean by finite deregular trees. So if I say finite deregular tree, I mean a finite deregular tree where the vertices has either valency d+1 or valency 1, so they are a leaf of the tree. So as you can see here in this example here is fine because these vertices have valency 3, so this is a 2 regular finite tree. So these 2 vertices, they have valency 3, but and all the others are leaf, so they have valency 1. So this one, this one, this one, and this one. But now here there is a problem because this vertex is fine. So this vertex is fine, it follows the rules. But now here there is a problem because this vertex is not a leaf and is not complete. So there is not a complete system of neighbors here. So when I say finite deregular tree, I mean something like this. Okay. Now let's do another remark. if I start from a irregular tree, I can always, and I have an automorphism of the tree, I can always induce a homomorphism on the boundary of the tree. Okay, this is the remark. Let's go through it. Firstly, what is the boundary of the tree? So the boundary of the tree is defined as following. So whenever you start from, so suppose that you fix a vertex V, so you can start walking from V through the graph, through the tree, in any of the direction you choose. So for the first step, I have 3 choices, then I have 2, then so on. And then you start building some kind of path. This is array. You start from V and then you go to infinity. And you can do the same for any other possible, let's say, direction in the tree. So if you visualize this let's say sphere around, let's say sphere around the tree, what is happening is that, let's choose a color. So what is happening is that in the end, all these directions are going to give a point that we call an end. So you have these, so the ends of the tree are these infinite rays that are starting from V and then they are infinite, so they just follow some direction. And then you define the boundary as the set of all these infinite rays. And as I said before, you can picture the boundary in your mind as this sphere, and then you can see here the direction these paths are pointing to. Okay, this is roughly speaking the idea of what is a boundary. Now, if I consider, yes?
Is V fixed? Is it distinguished, or?
So the fact for the moment, of course, in order to give this definition, I need to fix V, but of course, it is independent on the choice of V. So you can just prove that if you change V, then you get the same boundary.
Okay.
So, okay, because the thing is that even if you change the point, the initial point, then you will always have this finite piece here, which is connecting the two, let's say, distinguished starting points. And this is not going to change what is happening at the infinity, because this is from the large scale perspective, you care about what is happening here. So if something small is happening in the core of the tree, you don't care because it's finite. So you want to see what is happening going to the infinity.
Okay, thank you.
Welcome. So yeah, this was not very precise as a definition, but you know, I just want to define this group, so I need to jump on some details. Okay, so this is the boundary. Now, if we consider phi an automorphism of the tree, you can imagine that phi is going to move the tree. But then, since it is moving the tree, it is moving also the boundary, because probably is sending this ray over some other ray somewhere. So phi induces, let's say, phi tilde in the group of homeomorphism or delta tau dt. I'm not saying now that the boundary is a topological space, you can have a topology, but all these things, you know, you just believe in that for the moment, and but it's easy to see how a permutation of the tree is going to give you a permutation of the points of the boundary. So, but Neretin's group are not just these. So Neretin's group, let's go back. So the Neretin group is going to be the group of spheromorphism. So actually it is going to be a subgroup of homeomorphism of the boundary. This is why we say spheromorphism. So this group I'm going to define is going to be contained here, and it is going to contain the automorphism of the tree, but it's going to be a bit larger. So let's see how. We think about breaking the tree in pieces. What do I mean? I mean that I choose, so let me see if I can be, can do something decent with this. So we start with a irregular tree, and then we choose a finite subtree, which has to be irregular as well inside V. So let's take something easy, which is this one. And then I want to break the tree, so I'm going to cut off this finite tree from the irregular tree. So if I do something like this, no, I cannot do that. Okay, let's try again. So now I want to cut this finite tree away, and what do I get? Now I get a forest. So this is a this is a set, a graph which is formed by union of these joint trees, and now you see that these trees are still regular, but they are rooted. So now, what can I do? I can consider phi. So if I call this tau d minus f, and this guy here is f, I can consider a phi which is in the automorphism of the forest. Since the forest has the same boundary of the tree, so you can see it here. So what is happening at the infinity is not changed because I had only a finite piece, cut it off, but so the boundary is the same. This is still the boundary of the tree, but now I'm considering an automorphism of the forest. So it's like a piecewise automorphism of the tree. This is going to do the same trick. This is going to induce something here. But now, if I consider the set of all possible automorphisms or homeomorphisms of the boundary that are coming from automorphism of the forest, then this is larger than what was happening here, because now for the forest I am allowed to move one piece. So I can move one piece, one tree over some other tree without caring about the structure that we had in the finite subtree that had cut it off. So in some sense, this is still an automorphism of a tree, or it is not, but it's very similar. It's just that I don't care about the adjacency relation that is has to be inside a finite subtree. So this is why you can start, in some sense, breaking the tree, because you are not respecting anymore the adjacency relation everywhere, but you are doing that outside the a finite subtree that you fix. So this example here is also a very nice example because I'm taking just the automorphism of one forest, but I can consider different subtrees, finite subtrees. So I have different forests, and then I can map one forest to the other if it is possible, and then look at which kind of homeomorphism I get there. But so the detailed definition, you can find it on the notes, but what I wanted to say is that now we got a group, because it's possible also to composite these elements here. Now we get something which is called narrating group ND, and this is contained in the homeomorphism group of the boundary. And this guy here contains the automorphism of the tree as a subgroup. And how do you topologize the narrating group? So you have two choices, or at least as far as I can read here. You can start from, so this is a topological group. And this is also a topological group. And for the moment, this one is an abstract group. And I want to topologize it. So I can steal the topology from the larger group. So I can consider the subspace topology from here. But this topology is not going to be locally compact on ND. So it's going to be a topology, it's going to give me something, but it's not going to give me something that is my category. So I don't like it. The other thing that we can try to do is to use the topology that I have here, which is TDLC, and move this topology around in ND in order to create a group topology there. So this is possible. So you can, in the end of the show, you can prove that there exists a unique topology on the narrating group such that the automorphism of the tree is an open subgroup of ND. So you can do this. And this one is an open subgroup. So this is a neighborhood of the identity. So each open subgroup of the automorphism group of the tree is going to be open again here, and things that are compact are still compact. So since this one is TDLC, then the neighborhood basis coming from the automorphism of the tree will give you a basis at the identity formed by compact open subgroups. So you are inducing a totally disconnected locally compact structure on ND. So this is the trick. If you can find a nice way to have a totally disconnected locally compact group embedded as an open subgroup in your group, then you just got that also this group is totally disconnected and locally compact. And this is a very nice example, and it is very important in this theory. So even if it is probably I was not so clear, but I wanted to invite you to explore Neratin's group. So this was my intention for the last part of the lecture. Hopefully it went not so bad. Okay, I stop here and thank you for your attention.
Thank you.